Now that we've seen recursion used for a couple of different, rather simple problems, let's tackle something a little bit more complicated, something a little bit more interesting. Let's go back to the problem of maze traversal. Now, if you think back to earlier in the course, you may remember we had a chapter or a unit on stacks where the application right was that we had this maze and we wanted to start at some place and then go to some endpoint. And the way we did that is we used a stack where every time we were exploring around and we saw some place that we could visit, right, we pushed it onto the stack, right. So we were using a stack data structure to keep track of where we were, where we could be in the maze, right, and we used that to kind of find our way out. Well, one of the kind of the parts of recursion is that recursion includes a built-in stack, right? It actually lets you use the call stack more directly, right, than you normally do with methods, right? So it's kind of it gives you another place to store information, right? Because a method calls itself, and then when it calls itself, it'll use different parameters. It's almost as if those parameters are going on a stack. It's like it's keeping track of what are the values, right, that need to be computed, right. So if you think back in your head to when we did factorial, when we did sum, there was this kind of this chain of methods that are being called, right, or there's a stack of methods being called, right, where first we were looking for this one, then we're looking for this one, then we're looking for this one, right. So the parameters are different for each call. Well, those things were basically stacking on top of each other, right? As something calls something, calls something, calls something, and then once we get to the end, right, it collapses back down, right, and all those calls return and they go away. But there's actually a stack there, right? So part of recursion is that we can actually replace the use of a stack with just kind of a recursive method, right? Use the stack that's built into the way Java executes or runs methods. So that's what we're going to do. We're going to try and redo the maze traversal algorithm from that earlier chapter that uses the manual stack with a recursive solution, where the stack is actually kind of implicit in the different calls that'll happen. So as we look at this, what we'll do is we'll actually start at one place and we'll make recursive calls and say, okay, make one step, then see if you can path find from that point to the end, right? So do a little bit of work, right? Take one step in your maze, and then recursively look for a path to the exit from that little step you took, right? Do a little work, then check for the exit. Now, there are kind of two base cases here, right? First one is, well, the one I just described is finding a solution, right? You're able to walk, take these steps to the maze, and then eventually you get to the end point, right? So that's going to be one way their algorithm stops. The second way is if the second case, right, is if we run out of paths, right? We have kind of ourselves blocked in, right? There's nowhere to go, right? That's the other case that may happen. So here we are over in NetBeans. I think what we'll actually do, I do want to go through the code line by line, but before we do that, let me actually try just sketching out by hand what the results will be. So just to give you kind of an idea of what this algorithm is going to do that we're looking at. So over here I have a very simple maze, right? So this is one of the sample inputs, and you can find it in the source code that's associated with the book. So imagine we have this maze here, and we're going to see if we can apply kind of our new idea of how to solve this. So let's say the following. I want to start at the first position, right, 0, 0, and then go down over here, right, position 4, 4. So this is my initial map. 1 represents an empty space, 0 represents a wall. So initially, what I can think of is that I want to make a recursive call that's going to start at my first position. So initially I'll have this, traverse of 0, 0, right? So imagine this is the first call to our method, right? So imagine we're running this algorithm. And I'm going to actually go ahead and open up the maze solver just on the left-hand side. I'm not going to talk about it just yet. But maybe if you kind of glance back and forth between us simulating it and the code over here, it'll be a little more clear. All right, so initially we run traverse on 0, 0. So let's copy our maze code. What will happen is this. First thing is we'll mark it as being visited. So we'll set that first point, 0, 0, to be 2. That assumes, of course, right, that we were illegally allowed, right, to traverse that spot, right? There wasn't anything already there. We hadn't already tried it. So far this looks like our algorithm before. But what happens is this. We're going to make another call. So we're not going to push anything on a stack explicitly. We're just going to go ahead and make another call to explore deeper in the maze. So over here, I'm now going to explore 1, 0. Well, that's going to make me look at this second element down here. I'm going to update the map here, so let me copy this over. But something else is also kind of happening in the background, and that is the call to the original traverse still exists, right? So I still have somewhere, right? I have a call to traverse of 0, 0, and then in the process of running traverse, right, I call traverse again. So now I have a method call inside of a method call. So I have a method call traverse 1, 0. And I have my maze here. So I go again here, and this space is a valid space for me to be in. So I'm going to go ahead and put in a 2 there, right? So it represents that I'm visiting it. So this is actually, if you look on the right-hand side, this is actually giving me a trace that says where I came from, right? So I started from 0, 0, then I went to 1, 0, right? So it's actually building the path here in terms of the parameters that are going towards this traverse method. So now I'm over here, and I need to continue exploring. Well, again, we're going to go and do another traverse, and we'll actually try a traverse on 2, 0. We're going to go down again. There's these rules over here. If you look at where we say, oh, go down first, then go right, then go up, then go left. These are the order, right, in which we try to traverse things. So normally, right, we would go and try to traverse 2, 0. But the thing with 2, 0 is that that's where I have a wall, right? There's a 0 there, so I can't actually traverse that, right? So this doesn't work. Okay, what do we do next? Well, the next thing to try is traversing to the right. So over here, we want to go to 1, 1. Looking over at my map, there's a empty space there, right? There's a number 1 there, so I'm good to go, right? That's a space I can try. So let's paste this over here, and then I'm copying over here, right? Remember, this is a recursive call, so the calls to the previous spaces, those are still out there. So over here, right, I want to go traverse 1, 1, so I'll go ahead and update this, right? So this now has a 2 to represent that it's a space I've tried. So we've made a little bit more progress. We need to call traverse again, right? We're still exploring, right? We haven't gotten to one of our base cases, right? We haven't gotten to a place where we're stuck. We haven't gotten to the end. So we call traverse again. This time, right, traverse is going to be called on 2, 1, right, as we're moving down again. So 2, 1 is this over here. This space is free, so we're able to traverse there. So I'll set this equal to 2, and then I need to copy this stuff, right? I still have those recursive calls in the background, so I want to keep track of those. Again, we're just extending our path. So right now, we're here at 2, 1, so we need to traverse again, so we'll go down again. So let's just copy this whole thing, I suppose, be the easiest thing to do. We'll have another traverse. 3, 1, right? We move down by 1. This is now 2 over here. Again, we're going to do another traverse. The rule is try to do your traverse by starting to go down, otherwise go right, up, left, right? So the rule is start with down. So over here, right, we're going to do a traverse on 4, 1, right, as we try to move down. And I guess we could copy this whole thing again. Let's do that. 4, 1. Copy our little maze. Over here, this goes to 2. There is an issue here. This is going to be one of our base cases. So one of our base cases says that if we get to some place we can't go any further in, right? If we can't go left, up, or down, right? Meaning there's a place we haven't explored, right? That's not occupied by a wall. If we can't do that, then return back by 1, right? So throw away that step you took, right? That was a step in the wrong direction. So that's what's going to happen here, right? Is that because we're boxed in, we hit the base case, and we go backwards. So let's copy this. And we're going to go back to the call to 3, 1. And let's mark over here. Let's say this didn't work. It doesn't work. So that doesn't work. Well, if that doesn't work, what we want to do is we're going to go to the right. So in this case, we'll go 3, 2. That means I need to go over here and update this one to be a 2, right? So now I'm over here. So we're good to go still. Let's go ahead and copy this again, right? So imagine another recursive call is being made. So we're sitting right here. We can't go down, right? So that doesn't count at all. But what we want to do, right, is we want to go right again, right? That's the second place we try. So let's copy this. And we'll go over here, indent this, and this is going to be now 4, 2, right? So we're taking one step to the left, or one step to the right, which gets us over here. At this point, we're almost done, but we still haven't hit the base case that says you're at the exit. So we gotta keep on going. So let's copy this again, simulate another call. So we're at 4.2 this time. We want to take another step. First rule is we go down. So can we go down? That does actually work for us. So let's go. Then let's go over here and update our maze. So we have a 2 over here, right, to represent that traversal was called. So we're not quite done yet. It's going to be the last step. We need to do one more traversal call. So we're here. The rules say that first we look down, then we look right, then we look up, then we look left. So here, right, there's down isn't valid, right? That's off the map, so we can't go there. But the next thing we do, right, is we look to the right, and that's a valid place to go. So let's copy this. Go over here. All right, so do another traverse, and this time, right, we're going to have our 4.4, right, our ending point, right. We're finally going to be at the base case. So 4.4, that's a valid place. Change that to a 2. So at this point, we've finished the process of finding a path through this maze, right. Initially, we started with traverse of 0, 0 to represent that we started over here, and then we've gone to traverse 4.4, which was essentially taking a step onto the place that I wanted to finish. So we found our path. We only had one little dead end here that we couldn't actually use. One thing we might want to think about doing, in addition to just checking to see whether a path exists between 2 points in a maze, is being able to print out the nodes or the cells, right, that we had to go through in order to get there. Now, one approach, right, might be just to loop through this thing and print out all the cells that are 2, but that's not quite good enough, right? That prints out everything that was visited. It doesn't just print out the specific path that did succeed, right? It prints out all of the places we had to backtrack from. So how can we address that? Well, it turns out the recursion helps us a lot here, because on the stack of calls, right, all those different calls that were made, that's actually a list of all the cells that were visited, right? So we started at 0, 0, we went to 1, 0, went to 1, 1, went to 2, 1, went to 3, 1, went to 3, 2, went to 3, 3, went to 3, 4, went to 4, 4. Those are all the cells we visited in order to get from the start to the finish. Now, over here, I do actually have still this 4, 1, which was a space I shouldn't have moved to, right? It was a dead end. But actually, right, because of the way the algorithm is set up, this thing basically just disappears. So I could actually even delete this line. And that'll actually give me my exact trace, right? So this is now somehow a list, right, of all of the places I visited to get from the beginning to the end. So if I have my recursive calls like this, what I can think about doing is at the end of each call, setting that particular cell, right, 4, 4, 4, 3, whatever, equal to a number that indicates that that was a place I visited in my solution, right? So let's try working through that. So let's copy this, go down here. So let's say 4, 4. We're done finding our path. We're returning, right? We're collapsing that huge amount of calls that we made. So let's delete that, right? So we're getting rid of that. And the finishing touch that it leaves behind is it puts a 3 in the maze to represent that, 4, 4 is the place I visited. So we can do that. And then we repeat that, right? So for 4, 3, we delete that call, right? We finishes out. And we put a 3 over here in our little map. Do this again. Different call, 3, 3, delete that. Put it in our little map. Again, this time we go 3, 2 over here, put that in our map. So that's good. Now we go 3, 1, again we'll delete and update. Now over here, what you'll notice, right, is that I'm not going to mark this 2, right? The call that went to the 2, essentially that's been forgotten about, right? Really only the calls that lead us to the successful path are the only ones that are actually going to be on this tower, right, that we're calling. Those are the ones that are on there are only going to be the successful ones. If any of them fail, they'll actually go ahead and return, right? So they'll be removed from that stack of calls. So this one we won't mark, right? Instead what we'll do is we'll mark 2, 1, right? So this one over here is going to update. Copy this, go down. So this is one we got rid of last time. Over here I have 1, 1, so I'll go ahead and update that. Delete out this. Then call this again. Right, well, not call this again, but collapse this again. Right now it's 1, 0, so we put in a 3 over here. Delete this. Then my last call, right? 0, 0. So last thing, mark that as 0, delete that. So this is my end result, right? I have my map here. And the zeros, right, we said those represent walls, so those are places we can't actually, traverse through. The one, right, is an empty space, right, an empty space that I did not actually visit. The three, right, is a space that I visited and was a space that I had to visit along the successful path, right? It's not just a dead end. It's actually part of my real successful path. Over here, we have just kind of this one straight 2 because that 2 represents that at one point in time when I tried that cell, but that cell was a dead end, right? I wasn't actually able to go from there to the endpoint. And because of the way our calls were structured, right, because they look like this, right, we only end up marking, those ones that were actually used with the 3, right? So that 2 will stay here, and we'll actually be able to see the real path in our graph. So that's kind of an overview of how this algorithm looks. So let's go ahead and take a look at the code for this thing now that we've seen a basic review of how it works.